In the previous part of the topic NMR spectroscopy, we have understood about the basic principle and the instrumentation involved in NMR spectroscopy. In the part 2 of this lecture series, we are going to understand what chemical shift is and how the chemical environment of a nucleus affects the magnetic field at which it is absorbed. We will also cover the applications of NMR spectroscopy in this lecture. Myself, Mamta Sethi. To read about these topics in details, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. So let's start with the topic NMR spectroscopy part 2. Okay, so let's understand the term chemical shift. So we all have understood in the previous presentation that how when kept inside the external magnetic field, a bare proton shows its NMR signal. But we all are aware that we are not going to, record the spectrum of a bare nucleus. We are of course going to note down the spectra of a molecule. And in most of the organic molecules, we know that carbon, hydrogen, oxygen and nitrogen, these are the nuclei which are present in any organic compound. And we are also, at the advantageous end that out of carbon, nitrogen and oxygen, only hydrogen absorbs and show the NMR signal. Now, we know that a bare proton, when kept in the magnetic field, will absorb at a certain strength of the magnetic field, at a certain frequency it will absorb. But when this nucleus is a part of a molecule, it is surrounded by so many other atoms and there are so many electronic and inductive effects which affects the absorption of this nuclei. So in nutshell, we can say that the chemical environment of this nuclear affects the position of the signal. Position of the signal, by this we mean that it affects the strength of the magnetic field at which we will observe the signal given by that proton. So let's understand that how when placed in different molecules, a proton gives signals at different magnetic field strength. So let us suppose that a proton, when it is present alone and when it is present in a molecule, there is going to be difference in the strength of the magnetic field. Sometimes it may require higher magnetic field strength in order to show absorption, or sometimes it may require lesser magnetic field in order to undergo the absorption. So this relative value of the strength of the magnetic field is quantitatively expressed by the quantity which is called as chemical shift. So if we want to define the chemical shift, basically it is the difference between the magnitude of the magnetic field. So it is difference between the B naught, the strength of magnetic field at which a free nucleus absorbs and at which a nucleus which is part of the molecular framework will resonate. So we call this quantity as chemical shift. We denote it by symbol delta, and it is numerically equal to the difference of the frequency at which the sample, which is our target sample, desired sample of which we want to record the spectrum, and this is the reference. Here, reference, we are talking about the bare nucleus, and the difference of the two divided by the frequency at which the reference absorbs multiplied by 10 raised to power 6. So the units in which we are recording this is going to be parts per million. So delta scale, we absorb this quantity in the units of ppm. This can also be written in terms of magnetic field, since frequency and magnetic field both are directly proportional to each other. So we can write it as B sample minus B reference upon B reference, which is again going to give us the same quantity, that is chemical shift. So after having understood about the term chemical shift, we now can understand how do we calculate this chemical shift. Before I tell you the calculation of chemical shift, let me tell you the fact that why do we measure the chemical shift, or why do we express the chemical shift in delta units, is because in units of delta the chemical shift is independent of the frequency of the instrument. Whether we are going to use the 60 megahertz instrument spectrophotometer, or we are going to use 100 megahertz spectrophotometer or 300 megahertz spectrophotometer, the value of the chemical shift in delta is going to remain same. So how do we calculate this delta? Is we write here the observed shift. Observed shift means at which a particular nucleus will absorb, divided by the operating frequency. This is going to be the frequency at which a particular instrument work, and multiplied by 10 raised to power 6, again to convert it into parts per million. So suppose on a 60 megahertz instrument, a proton absorbs at 60 hertz. So we can calculate this delta by dividing this frequency at which a particular proton absorbs by the frequency of the instrument, which is 60 megahertz, that is 60 into 10 raised to power 6, and multiply this quantity by 10 raised to power 6 to convert into ppm. So this comes out to be 1 ppm. So on a 60 megahertz instrument scale, delta equal to 1 ppm means that a proton is absorbing at 60 hertz. Now the same proton, when we record the spectra using 100 megahertz instrument, will absorb at 100 hertz. So how do we compare this 60 hertz or 100 hertz? Is again by converting this into delta, that is chemical shift. So on a 100 megahertz instrument, this is the frequency at which the proton will absorb, that is 100, divided by the frequency of the instrument, operating frequency of the instrument, multiplied by 10 raised to power 6. So we can see here clearly that it is also coming out to be 1 ppm. So this is the advantage of expressing the chemical shift in terms of delta, because it is independent of the frequency of the instrument. So this scale is universal, we can use it, right, anywhere. And also, we want basically chemical shift to depend upon what? Different nucleus. So it depends upon, chemical shift depends upon the environment in which a particular nucleus is present, and not on the frequency of the instrument. So now we have understood how do we calculate this chemical shift. And in the formula of chemical shift, if we remember, we have seen that it is the difference at which the proton in a sample absorbs and the reference. So what is reference? So the answer to this question lies in the fact that why do we need a reference? So we need a reference because we then want to compare that at what magnetic field strength a bare nucleus will absorb and a molecular nucleus will absorb. But we cannot choose a bare nucleus as reference. We all know that it cannot be chosen, it is not. So what do we need? That means we need an internal standard, or what we can call as a reference molecule, with respect to which we can measure and express the chemical shift of various molecular nuclei. So this reference in NMR spectroscopy is the best reference that we are using most of the time nowadays is TMS. TMS stands for tetramethylsilane. So this is a very commonly used internal reference. The structure of tetramethylsilane is shown here. We have 4 methyl group which are exactly in identical environment, and it is this fact which is which plays a vital role in deciding why TMS is used as a internal reference. So since I mentioned that it has got 12 equivalent protons, so all protons which are equivalent will give rise to only one signal, and since this signal is due to the presence of 12 protons, it is going to be a very sharp signal, and we will have a one sharp signal. We can place it at the reference at the extreme right hand of the delta scale, that is the scale that we use to express the chemical shift, and all other molecules will show the NMR signal on the left hand side of this tetramethylsilane, that is your reference. There are other reasons also why we choose TMS as internal reference. One, of course, is that it is unreactive. Now we don't want to spoil our sample. We want that whatever reference we are using, it should not react with the sample, otherwise it might affect the spectra of our desired molecule. So this is very unreactive molecule, so it does not react with our sample. It is extremely volatile, so it can easily be recovered from the sample and we can obtain the pure sample again, and it can dissolve. This again, that our sample should be soluble in, this should be soluble in most of the organic solvents. So this TMS is soluble in most of the solvents, and it also absorbs at higher field. This part I will cover in the next slide, that what do we mean by higher field. So higher field, and just for now we can understand that higher field, that it is going to show the absorption at extreme right hand of the delta scale. So let's understand the phenomena of shielding and deshielding. So as we have understood that a proton, when it is present inside a molecule, it has distinct chemical environment. It is surrounded by so many electrons, right? So these electrons are also what? Charged particles. So just like nucleus, these electrons will also start expressing or start experiencing strong magnetic field. So now when external magnetic field is applied, so along with this the proton, these electrons also start circulating, right? So these circulating electrons will generate their own magnetic field, right? So depending upon the fact that these electrons are what? They are in a way acting as a barrier or acting as a shield between the external magnetic field applied and the field which is really experienced by this proton, which is surrounded by these electrons. So these electrons basically shield the effect of the magnetic field. As a result, the magnetic field which this nucleus will observe will be lesser than the applied external magnetic field, and this phenomena is known as shielding. So these electrons, and as the electron density increases in the surroundings of a particular nucleus, then of course the strength of the magnetic field that it is going to experience will decrease. So what we will have to do is, we will have to increase the strength of the external magnetic field. So suppose it was in the on a 60 megahertz instrument, a bare nucleus absorbs at 14,072 Gauss. That is the strength of the magnetic field which is required for a proton to flip at a 60 megahertz instrument. But since it is now going to be surrounded by these electrons, so owing to the presence of these electrons, the effect of that magnetic field will be less, and therefore we will have to strengthen the magnetic field further, and it will absorb at a higher magnetic field than 14,072 Gauss. So this phenomena is called as shielding, and this is due to the circulation of the surrounding electrons which are present over here. So now there is a closely associated term called deshielding. So just now we have understood that the electrons which are present in the surrounding, they generate their own magnetic field, and this field shield the strength of the external magnetic field which is experienced by the nucleus. Now there are two cases. This this is known as induced magnetic field. The field which is generated by the circulation of these electrons is called as induced magnetic field. There arises two cases. The induced field might be in the direction of the external field. So if this is the direction, so if the induced field is in the direction of the external magnetic field, this is going to reinforce the effect of external magnetic field, and if this is against the direction of the external magnetic field, it is going to reduce the effect of the external magnetic field. So in this case, where it reduces the effect of external magnetic field, this phenomena is known as shielding, and where it reinforces the strength of external magnetic field means that the field experienced by this particular nucleus is going to be what? Lesser than the strength of the external magnetic field, because this field which is due to the presence of these electrons is in the same direction. So this phenomena where the field reinforces is called as deshielding, right? So deshielding and shielding plays a vital role in deciding that where a particular nucleus will absorb and show signal on the delta scale, and what is going to be the value of its chemical shift. Now we have understood, so this can be very clearly explained, the phenomena of deshielding which is present in alkenes through this diagram, where we can see that this is the direction of the external magnetic field, and these loops indicate the circulation of the electrons. So this is the induced magnetic field which is generated due to the circulation of the electrons which are present. So this is due to the circulation of pi electrons which are present in alkenes, and we can see that the protons are present in this region, right? So the protons are present in this region, and in this region we can see the arrow. This is the direction of the induced magnetic field. So we can see that where the protons are present, the direction of the external magnetic field and of the induced magnetic field is what? It is identical. So this induced magnetic field is reinforcing the external magnetic field. So this phenomena, as we have just understood, is called as deshielding. So in this particular case, we need to apply lesser external magnetic field for the nucleus to show absorption. And in this case, deshielding, and then this is expressed as downfield. So let me draw just very briefly. This is going to be our delta scale of chemical shift. This is the extreme end. This is delta equal to 0 is assumed to be at a position where our reference, that is TMS, absorbs. All other molecules will show absorption to the left hand side of the signal of the TMS, right? So if a molecule, if in a molecule there are deshielding effects, then deshielding, this side, left hand side, right to left is deshielding, right? So deshielding means this is known as downfield and delta. Deshielding, downfield and higher delta value. The value of the delta is increasing from right to left. And if we have the induced magnetic field, which is against the external magnetic field, that is known as upfield. Upfield, that means low value of delta. So delta is for downfield, delta value is high delta. So based on the different values of the chemical shift, different molecules can be distinguished from one another, and we can characterize the organic compounds. So in the first part of the presentation, we had learned about the concept of shielding and deshielding, and how shielding and deshielding decides that what value of a chemical shift will a particular nucleus which is present in a molecule will absorb. So in the next part of the presentation, I am going to describe the the spectrum of ethanol molecule, through which we can learn about the various concepts which are involved in NMR spectrum of any molecule, and finally we will also understand the basic principle of MRI scan. To read about these topics in details, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. If you like my video, please like, subscribe and share. Press the bell icon for future notification. Thank you.
Without the permission of the copyright holder.